Well, I'll now show you a method or function which will basically get rid of the problem which we faced due to the outliers, right? So there is a function called as a sigmoid function, okay? And the sigmoid function looks like this. I'll just show you the plot of it. Google, I think it plots whatever I'll give. I'll just check it out. 1 by 1 plus e of minus x. Uh, well, I think it will be exp of, yeah. Now see what it is actually a sigmoid function given some x. If we take the sigmoid of x, the function is like this, okay? That means what was the problem with the outlier? If you remember, because of some greater value, our classifier was confused in taking the decision, right? So it was misclassifying something, or it was going towards the wrong direction, right? Because it was basically due to the outlier point which was at a higher distance than the other points, right? That was the issue. Now how do we solve it? We basically taper it off, we squash it, we'll use some squashing function, okay? So we'll squash the value in some range, because the outlier points can have any value, right? It can have positive infinity, it can have negative infinity. That is normal. So it can be very high value, but we want to taper off the values, okay, in a certain given range, okay? Because in reality we can have anything between minus infinity and positive infinity, and we have already seen, due to the problem of outliers, if the values are very high or very low, then our classifier actually gets misleaded, right? So what we want is, we want to bring the values in a certain range, we want to squash the values, and that is what a squashing function is used for. And the best one here which we'll be using is the sigmoid function, okay? You can see the sigmoid function. You see here, for small values it is basically increasing in a, I'll just use a pen, yeah. So for the small values, it is, you can see this is linearly increasing. That means for some value, say for 1, it will give the output as 1. For maybe small values like 2, it will give the value as 2. It is increasing linearly. But for higher values, you see, greater than this particular point, you can see it is tapering off, okay? That means it is tapering off. What it means is, it is basically squashing the value in a certain range, no matter what the value is. Let's say the value is 12, it doesn't matter, the output will be 1. You see, this is 1, right? So what is the range of the sigmoid function? It is from 0 to 1. That means the original range was from minus infinity to positive infinity. Now what this sigmoid function is doing is basically squashing the value within, or it is bringing all the values in the range of 0 to 1, okay? In that way we'll have no problem with the outliers. That is what is our goal. So we'll be using the squashing function, which here specifically we'll be using the sigmoid function for it, okay? So this is you can see this particular values. You see here for it is 0.5, okay? And for the negative values it is again going towards 0, right? That is, all the negative points will be, very high negative points will be tapered off to 0, and all the very high positive points will be tapered down to positive 1. That is, it will bring in the range of 0 to 1. That is what this particular function is doing, okay? And there is some speciality for using the sigmoid function, and I'll be talking about that in some next videos, in some later videos, okay? It has some probabilistic structure which will be helpful. That is why we are using it, but I'll talk about that in some later video, but right now you understand that this particular sigmoid function can be used to solve the problem with the outliers. Okay, now how will you use it? So what is a function? If the sigma of x is basically nothing but 1 by 1 plus exp of minus x. Okay, this is the sigmoid function. Now what was our original function which was having the issues? We had this, right? So just we'll write it, say w star is nothing but the optimal w is basically equals to we wanted to maximize, right? Maximize what? Maximize the summation of I equals to 1 to n, and we had yi w transpose xi, right? This is what our equation was, but this was prone to outliers. These are problems with outliers, right? So we'll just modify it to something called as like this: w star equals to max, that is fine, max on w basically, I equals to 1 to n, but here we'll be using the sigma of this yi w transpose xi, right? So now you see the result will not be different because the linearity of the function will make sure that the result doesn't get inversed or reversed, or it doesn't get something random, right? Because you see it is what it is basically doing. It is basically bringing the data in a given range. Okay, the positive values will be in the positive section only, right? The negative values will be in the negative section. It is only bringing it in a certain range. In the original data, the range was say minus infinity to positive infinity, right? Now what we are doing, we are simply bringing it down. That doesn't mean the negative points got in the positive side or the positive points got in the negative side. No, that didn't happen. We are simply squashing it, means we are pressing it down. Okay, that's it, nothing else. So the result will be same. Don't worry about the result. Okay, now you see, after we have used this particular sigma function, what will be the equation? So max w, I'm just deriving it from the start, so that you don't get confused. Okay, I'll not do any step jumps. So sigma, this is the sigma of x. So what we can write here is 1 by 1 plus e of minus yi w transpose xi, right? We can write this. Okay, now you see there is a function called as monotonous function. What is monotonous function? It means, say, log of x. Okay, if x increases, log of x also increases. If x decreases, log of x also decreases. That is the beauty of log function. Okay, so till we have this particular property of monotonically increasing or monotonically decreasing function, we can say the result will not vary, right? If we use log x instead of x, we will be sure enough that the result will not be different, because say the x is increasing, log x will also be increasing. If log x is decreasing, if x is decreasing, log x will also be decreasing. So no matter what, the result will be the same. So we can very safely use this particular, pardon my handwriting, I'm worse than a doctor. So I'll just use the log function here, right? So I'll write log of 1 by 1 plus e of minus yi w transpose xi, right? Now what is log of 1 by x? We already know it, right? Log of 1 by x is minus log x, if I'm not wrong, right? So we can rewrite this equation as this will be basically inverted and minus log x. So we can take a new page and w star equal to maximize w on I equals to 1 to n minus log of 1 plus e power e of minus yi w transpose xi, right? This is what we can get. Now this is a maximizing function, right? And here is a negation here. So what we can write here is we can simply make it minimize w. Okay, so I equals to 1 to n and log of 1 plus e of minus yi w transpose xi. Okay, we can do this. So we have converted the maximizing function to a minimizing function. That's what we have done here, right? Now we want to find the minimized value of this entire equation. Okay, so we need to solve this, and you can see that if we solved this, or if we have optimized this equation, and if we use it, it is prone to the outliers. Okay, so it will not have any effect of the outliers, because it is the squashing function. It has used the squashing function sigma here, right? Sigmoid. So we have converted the original equation to this particular equation, which is actually will work fine if there is outliers, or if there is no outliers, it doesn't matter, it will work fine. Okay, so I think that's it for this video. And yeah, so in the next video I'll be adding some extra things into this maybe, but this is the equation of the logistic regression which you'll be using, or which will be will be implementing in the algorithm of logistic regression. Okay, so this is the final equation which you need to use, but although I'll be using some component with it afterwards in the next video for overfitting and underfitting, for actually dealing with the overfit and underfit problems. But this is the crux of logistic regression. Okay, if you can understand the derivation of this particular equation, you better understand how logistic regression works. Okay, so thank you for watching this. In the next video I'll be explaining something extra with this. Thank you.